Hi, everybody. This is Colin McDamo, and we're going to be doing a demo of DVC and the R package targets. DVC will allow us to version our data sets as well as our models, and targets will allow us to create machine learning and data pipelines, as well as to scale our computations with ease. In case you're interested in follow along, I'm going to give a brief overview of my hardware and software specifications, although everything I'm presenting today should be fairly agnostic to my operating system, as well as the specific versions of software that I'll be using. In particular, I'm using an Apple M1 Pro MacBook. I'm using R version 4.1.3. I'm also going to be using Visual Studio Code to run my R code, as well as construct my targets pipelines. And I'm using the R language extension for Visual Studio Code. To kick things off, we're going to create a new repository. So I'm signed into my personal GitHub account, and we're going to fire up a new repository, and we're going to call this Stemaway targets demo. And I'm just going to give it a brief description, demo repo to showcase DVC and targets. I'm going to make this private for now. Eventually, I'll make this public. I'm going to add a README file. This is almost always a good idea. I'm going to also add a Git Ignore, and I'm going to choose a Git Ignore template, as they provide an R Git Ignore template that has many different files we're going to want to ignore. So if I go down in the list, I see that we have an R template already. In terms of license, at this stage, the specific license won't matter, although it's a good idea to get accustomed with the idea of adding a license in the event you do go on to commercialize the software that you create. So here, I'm just going to pick a general public license and move on. Go ahead and hit create repository. I see that here we have the newly minted repository. And the first thing I'm going to do is edit the Git Ignore file, because I already know there are a few patterns that I'm going to want to go ahead and ignore. So if I go ahead and click on the Git Ignore, on GitHub, you have the opportunity to edit raw files. This isn't necessarily a common practice, although it will speed things up for me to just do it here. So if I go ahead and edit this file, and add a few lines or patterns of things I want to ignore. So I'm going to go ahead and add a comment that I'm going to ignore my data folder. And I'm going to add the data pattern. I'm going to go ahead and ignore certain report patterns, reports, a wildcard operator, .html. So these will be my rendered reports that come out of R. Reports, another wildcard, .nb. .html. This is another R-specific extension of rendered reports that come when you preview different documents in mid-R. And I'm also going to go ahead and add the DS store, which is a common nuisance file that we don't really want to track that may be specific to my operating system. Okay, great. So we have the items that I wanted to get in there and ignore. I go ahead, the commit message is already good enough. It auto-populates with update git ignore. I'm going to go ahead and commit directly to the main branch instead of creating a new branch and starting a pull request, because I'm very confident in these changes. I'm going to go ahead and commit those changes. Briefly, I'll run through some items that are already inside this template file. So we see R history and R app history. It's fairly critical that these files be committed to the Git Ignore. The reason being, oftentimes in interactive data science projects, you type specific identifiers, filter for specific values, and in general, leak certain things by entering things into the R console. This is also the case with Python and Jupyter notebooks. So this is a language agnostic principle. Whenever you have an artifacted file that contains history of code that has been entered into either your REPL or your console or command prompt, you want to go ahead and make sure that all of that history is gone when you check things into version control. So we can see in the template file, the R history is automatically included in the Git Ignore, and that's fantastic. So we don't need to worry about that. Similarly, we have a .r data file. So in general, this is a catch-all file type where we do not want to commit the entire data workspace when we're working in R. Instead, we want to use a tool like DVC to be very principled in the way we go ahead and version our data. Also, user-specific data files, such as R user data, are important to ignore. And we can also see some other types of files. Here we see example code and package build process that may come when you're actually building R packages. Again, we see outputs from the R command build, etc. And so the rest of these are fairly self-explanatory. And if you don't recognize these, that's totally okay. This is just the overall template for what you can ignore, and you can mix and match based on the needs of your project. You may want to take a look at GitHub's proposed Python ignore files or create your own that you use as a template in general. Of particular attention is the R environment variables, Git ignore item, the .r environ. And this is incredibly important as well, because we do not ever want to leak our environmental variables and secrets into version control. So here it's just a single file, but there may be another directory, for example, a .env directory that we want to go ahead and add to this Git ignore. For now, it's beyond the scope of what I'm going to demo today. But whenever you have environmental variables or a consistent pattern with which you store your secrets, you want to make sure that that's built into all of your templated Git ignore files. Okay, great. So if we briefly take a look at our repository, we see that there was a commit 2 minutes ago that updated the Git ignore, and that's the only change we're going to make on GitHub itself. At this point, we're ready to go ahead and clone the repository. So we go ahead to code, copy the path. I'm going to go ahead and clone over HTTPS. Now, I've already instantiated my personal authentication or access token, and GitHub has phased out username and password authentication over HTTPS. So you likely need to do the same and set up your PAT on GitHub itself. Those instructions, if you're interested, I can go through, but that's also beyond the scope of this particular demo. So I'm going to go ahead and git clone, and we see that we've successfully cloned. So now if we change directory, Stemaway, targets, demo, we see that we have our repository ready to go, and we can get started here. Okay, great. So I have some pre-populated files that I've already created that would take a little bit too much time to write on the fly. So I'm going to go ahead and copy those over to our new repository. So let's go ahead, find our Stemaway targets demo. Great. So the files we're interested in copying over. Great. We can get rid of that. And the files that I've copied over are _targets.r. We have a data folder that has some CSVs and XLSX data. We have an R source code folder that has a functions.r file. And we have reports, which has regression diagnostics.rmd, which is a markdown file that when rendered creates an HTML report. I'm going to go through what this data is briefly to contextualize why we're doing this as a pipeline in the first place. So this data is sourced from the Cynthia open dataset, and this is a synthetic patient generation dataset that has some really cool science behind it. I highly recommend you check this out if you're interested in working with healthcare data or patient-centric electronic health records. And I downloaded their freely available open source dataset that again is synthetic patient data. And those are the files that we're seeing here in my data folder. They're broken down into conditions, encounters, medications, observations, and patients. We're going to be particularly interested in patients for the sake of this demo. But again, it's always a good idea to have a data folder that houses all of your data sets. Furthermore, in a real setting, your data folder should actually be comprised of multiple subdirectories, including your raw data, your intermediate data sets, your process data sets, and your final canonical model matrices. For the sake of this demo, again, we're going to keep everything as just a CSV. So hopefully that gives some context on the Cynthia dataset, and this is what we're going to be using here today. So now let's go ahead and open this in VS Code. So I'm already in the directory. I can use the code and then period command to open this repository in VS Code. So let's see what we have. We'll open functions.r. We'll also open targets.r. And finally, we will open regression diagnostics.rmd. First and foremost, let's take a look here at the changes. As I copied all of these files over, we see that all three are waiting to get checked into Git. We don't yet need to actually make this commit at this time, as I'll be making a few other modifications. Let's take a look at functions.r, as these are comprised of several different R functions. If you're unfamiliar with R and haven't really programmed with it to the extent where all of the syntax is familiar, that's totally fine. The point of this demo is not to go over R syntax, in that I've purposely picked simple R functions that should hopefully be self-explanatory. The goal here is to understand how to compose a machine learning pipeline and break down the different components in such a way that you have a feel for how you would abstract your entire data pipeline and how you can get your results structured in a way that affords this kind of extensibility that we've been talking about in the overall presentation thus far. So again, functions.R is comprised of functions, and these functions are the different components of our pipeline. Of critical importance is the underscore targets.R. Now, underscore targets.R is the critical file to build a targets pipeline. Targets is again an R package that allows you to create data pipelines, machine learning pipelines, and every single targets pipeline is always defined via this root level file called underscore targets.R. Now, underscore targets.R is a fairly straightforward file. You load certain libraries and global settings. Then you define any custom functions that didn't go into other source code files, such as functions.R. And then you also set the packages that will be used within your targets pipeline. In this case, I'm going to be using the data.table and per packages. So I explicitly direct targets to load these packages upon running any given instance of my pipeline. And finally, the most important piece, you end with a list defining your pipeline. So how do we define a pipeline? Well, we abstract the entire data science chain into a set of steps. Here in targets, we first name the given target, and we define what that target does. First, we see our target is raw data. And the definition here is simply a path to the raw data file, data patient CSV. By specifying format equals file, targets knows that this step or this target is defined via loading a raw data file. The next target is called make model. And the way make model is created is by running our function called get healthcare by age, which is a function of the raw data. Notice that raw data is referenced here as well as here. And this is what allows targets to understand dependency structures. Whenever we're designing pipelines, we always want to be thinking in terms of dependencies. What parts of inputs and outputs depend on each other? Where do we branch? Where do we induce conditional checks? And where do we merge back again? Most of us are aware that we begin with data of some kind, and we end with models, metrics, reports, and visualizations. But it's not enough to just know where we start and end. We need to understand what are the through lines of the analysis that form a dependency structure. So let's again move forward with the rest of these definitions. We then have summarize, which is defined by the function getModelSummary, which takes as input makeModel. MakeModel being a target that was previously defined in this step. We then have another target called getPredictions, which is defined by getModelPredictions, which takes as input makeModel. Notice that both of these steps or targets have makeModel as an input. MakeModel is what's actually generating our model. These two targets can be run independently because they don't depend on each other. They simply depend on makeModel being run and having valid results. Once that's the case, we can launch a job or process to run the summarize target in conjunction with the getPredictions target. One is simply summarizing our model, and the other is using the model as a prediction mechanism to predict on new data. Finally, but not least, we have a target called Diagnostics Report. And this report itself points to a file, reports regressiondiagnostics.rmd. Notice the outer function is different than the rest. Here we have tar render. And in targets, tar render specifically allows us to construct a target that is itself a report that may depend on upstream targets. With that, our pipeline is completed. Now, again, this is a very simplified pipeline that has some well-defined steps, no branching structure, no conditionals, but hopefully this helps motivate the necessity of using a pipeline even for the simplified example. So I'm just going to take a second here and allow you to absorb, again, this list and the target dependencies, and then we'll move forward. Okay, great. So one other thing I want to point out is in my functions.r, one of the most important functions is get healthcare by age. Let's just briefly walk through this structure. It's a function of patient data, and patient data in this case could either be a string or an actual data frame. This first conditional block checks, is patient data a string or character in R? If it is, we then read it with the fread utility, which is very similar to reading a CSV with pandas. Then we do some very light feature engineering and data cleaning. Then we do a filter step where we say the patient data is going to be assigned a filter of patient data where gender must equal F or female. Finally, to return a value in this function, we create model. In this case, it's LM, which is linear model or linear regression, where our outcome is the healthcare expenses variable, and our explanatory variable is age. The data argument allows us to specify what is the data set that's being used to formulate the linear regression. So hopefully this makes sense, where we're reading in data of some kind, and the final return value is itself a linear model. That linear model has many different methods attached to it. We can do things like summarize, we can do things like plot the regression diagnostics, and we can also predict new values using the model that we previously fit. So this function encapsulates the entire chain from reading in the raw data to fitting a cursory model that is just linear regression. One other cool feature about VS Code I'd like to point out here is when I hover over this line, we see that the linter has caught a potential problem. Here we see the commented code linter specifies that commented code should be removed. One blessing and curse of VS Code is that you can enable these types of linters that take principled stances on how you should format your code. Sometimes they catch actual violations of syntax, and sometimes they're stylized guidelines that may help with code clarity, create formatting standards, etc. Here, this is an opinionated take on what should be done to correct an issue. This says commented code should be removed, which is not a law, but it's a good suggestion. One problem that we as data scientists or machine learning engineers find ourselves in all the time is running an experiment, having a snippet of code that we comment out, and then having an alternate version of that experiment that we then have below the comment or above the comment. And this is a really dangerous game because it's very easy to lose track of, it's very hard to evaluate the impact, and the record keeping tends to be very poor when people comment out their code. So I would highly recommend, if this is a practice you find yourself doing, or when you investigate your code, whether it be your source code, your notebooks, etc., if you are finding that you have commented code that you're committing, you might want to take a step back and ask yourself, why did I have to save this commented code? Tools like DVC and targets were designed to mitigate this kind of problem, where you do not need to aggressively comment your code, try different experiments, have things be a hodgepodge of ideas that might be used for a particular run of a pipeline or script, but may not. So again, I recommend deleting this commented code, but I'm going to leave it now as a reminder, again, of why targets can be very useful in a setting like this. To briefly run through the other functions, we have getModelSummary, which simply creates a summary on a model object, which does things like calculate R squared, as well as characterize the residuals. We also have getModelPredictions, which takes as input the fitted model, and we create a locally scoped variable called newData that is simply a data frame with a single feature called age, where we sequence from 0 to 130 years old in steps of 5. We then call the predict method of the fitted model, and we have as input the new data. So we take this new sequence of age, take the model that was fit in the get healthcare by age function, and predict these new values. Finally, we have a function here called getGitTag, which actually creates a system call. This system call is not R code. Instead, it's actually a command you would run in Bash or a command prompt, here describing the most recent Git tag in whatever branch you're currently checked out in. So these are the sequences of functions that we'll be using in our targets pipeline. Again, I'm going to take a pause there and allow you to absorb the composition of these functions on the screen, and perhaps think of some questions you may want to ask in case anything is confusing, especially if you've never seen the R programming language before. Okay, great. So now at this point, we're going to go ahead and start visualizing our pipeline. Often it's very difficult to get a feel for a pipeline unless it's represented in some visual way. So in order to do this, we're going to go ahead and start a terminal. So this is the integrated terminal in VS Code. Right now I have my shell. I can add another shell, but we don't need those right now. I can also add an integrated R terminal. In this case, I'm using the Radian terminal, which relies on both Python and R. Radian has some big advantages over your vanilla R interpreter when you use it in your command line. And these include syntax highlighting, copy-paste features, and just a better sense of aesthetics and autocomplete in general. So again, this is the Radian R interactive shell. So first, I'm going to go ahead and call library and targets. In Python, this is akin to importing a module. Now that we've loaded the targets library, we can go ahead and call a specific function called tar viz network and inspect this function. So let's see, tar viz, and as we can see, Radian is going to go ahead and autocomplete that. So we see it's produced a visual in the interactive viewer. This is how Targets visualizes its pipelines. And there's a lot going on in this graph, so let's take it step by step. Every triangle is a summary that we see defined in this functions.r file. Every circle is a target that we see defined in the targets.r file. Let's just take a second and make sure that we can map from targets to the visual itself. We see make model is here. We see raw data is here. Summarize is here. Get predictions is here. And diagnostic reports, that is here. Go to functions.r, get healthcare by age, get model predictions, and get model summary, all of which are represented here. So we can see the dependency structure take fold. Make model the target depends on both the raw data target as well as the get healthcare by age function. And let's just verify to ourselves that that makes sense. In order for the make model target to actually be defined, we need to run this function get healthcare by age. In order to run that function, we need the target raw data to have already been defined. So as we can see, there are two directional arrows, both stemming from get healthcare by age and raw data in order to create the make model target. Now, if we look at Diagnostics Report all the way down here, what does it take to create Diagnostics Report? Well, it's a rendered HTML document, and let's trace backwards. Well, we can't do that from the targets definition, so let's go ahead and take a look at the actual markdown itself. Scrolling down, we see that we have r equals rev parse single get working directory head. We have these commands which are related to Git, and then further down here we see tar read. So this first chunk doesn't have any target specific code going on in it. It's actually just related to the Git repository. Further down, we see plot tar read make model. It is this line that induces the dependency structure between Diagnostics Report and make model. If we go back to our targets file, we see that when we look at this report, we actually can't tell what it depends on. Targets automatically infers this dependency that goes from make model to Diagnostics Report. And the way it does it is via static code analysis. It loads in regression diagnostics because it knows that it is our final target here. And it looks for references to existing targets within these code chunks. In line 31, we see that we are plotting the actual model itself. And we are doing that by using the tar read function, which reads in the result of a particular target, and it is reading in the result of make model. That is how we're able to infer, in order to generate this report, the following must happen in sequence. We must read in the raw data, we must load and source the get healthcare by age function, and then we must run this function with the data parsed in as the input. This allows us to create the model itself, again, a linear regression, and that model is a dependency of this diagnostics report, because in order to render the report, we need to reference the output or target make model. I'm going to pause here again and let you inspect this dependency graph or DAG and make sure that everybody is understanding how we're able to arrive at this kind of dependency structure. Okay, so hopefully this is making sense, and let's go ahead and actually create this pipeline. So we've defined it, we have a blueprint, but we haven't actually run anything yet. The way we do this in targets is by using the tar make function. Now, tar make has a few different options available. Here we're going to pick the tar make future option. We're going to run this with workers equals 4. Now, talking about future and parallel computing in R is again beyond the scope of this particular demo, but essentially targets allows us to parallelize for nearly free by using future, another package in R. By using the future backend, as I was referencing before, if 2 targets can be run in parallel, it's going to go ahead and assign available workers to actually run those targets for us in parallel for free. So instead of specifying all sorts of parallel options, by simply running tar make future with workers equals 4, we're going to get free parallelism when we can get it. Now, in the future of this demo, I may be running just tar make because this is fast enough to run without parallelism, but I just wanted to mention the fact that this is here and available to us. So I'm going to go ahead and run that, and we see we get some fairly informative output. So we see in targets when we start building a target and when we finish building a target. We see that here, that for example, we built the target raw data, and we see this with each of our targets. We also see the fairly verbose output when there are namespace conflicts, although that's always good to be aware of, that there may be namespace conflicts and we may need to resolve those manually. And we also see that the pipeline finished successfully, and it was built in 2.836 seconds. So targets is letting us know. Now, let's go ahead and run tar viz network one more time. Let's see what we get. Now, when we run it this time, we're going to go ahead and add a few options here. So we're going to give label, and we're going to plot a few specific items that help us interpret the overall performance and characteristics of this pipeline. And those labels are going to be time and size. Now, when we inspect this, we see a few things have changed. First of all, nothing is blue, and that's because every target is up to date. When you run tar viz network, it will show you what targets have been outdated and which ones are completely up to date. A target becomes outdated when you change something about the definition of that target. For example, choosing a different filtering rule, using a different piece of data to create a model, changing what you include in a final report, etc. Now, because all targets have just been run when I ran tar make future, everything is up to date, and this is the freshest possible instantiation of the pipeline we can get. Zooming in a little bit, we see that we also get a few things that describe the targets themselves. In particular, the timing, how long each target took to create, as well as the size of each target. How big is each target in memory? These help us profile potential bottlenecks or pain points in our pipeline so that when we run them, we can optimize further. Okay, great. So now we've run our targets pipeline, and there are a few things that have been created in the background while all this has been going on. So if we look, there's actually a new directory. We see that things in green are things that have yet to be checked into Git. So let's go ahead and check out what's in targets. There are a few things here. Targets has a meta folder, which has metadata that track how targets are changing over time and how the run of a particular target pipeline is going, in this case, progress. It has an object subdirectory, which has a file per defined target here, unless we have something like tar render. So here we see each of our targets here, make model summarize and get predictions, has its associated object in the tar objects folder. Now, this is the actual data file itself. You could read any one of these in any interactive R session, including one that is not tied to this R process, and get the version of that file itself. We also see that there is a specific Git Ignore. This is a theme that you'll see several times over, where there may be nested Git ignores for particular directories. Let's check out what's in this particular Git ignore in the targets folder. So we see there's a wildcard in the first line. When there's a wildcard here and it's freestanding, it means to ignore everything inside that folder. However, the exception to this is when we have an exclamation mark. When there's an exclamation mark, it means do not ignore this particular file. So of course, we do not want to ignore Git ignore. We also don't want to ignore the meta, but we do want to ignore things inside here. But meta itself, this piece of meta, is something that we do not want to ignore. So these two files can be thrown out, and we can actually see that this is the behavior that's happening from the Git ignore because meta is in green, it's untracked. And if we hover over either of these two, they're grayed out because they are ignored given the current definitional pattern of this nested Git ignore. So hopefully that makes sense. And again, if you have any questions, please ask me in real time. So this is really important because this also implies that in any project you may face in the real world, you may have competing Git ignores, and you need to make sure you understand where you're placing your Git ignores and what kinds of contrasts certain patterns or wildcards may create in a Git ignore. It's not enough to just look at the first line, for example, and understand the behavior of a Git ignore. You have to inspect whether or not you're reversing some rules that were previously declared with a catch-all wildcard pattern. So let's just take a second to make sure everybody is up to speed with this Git ignore, and I'm going to give that a few seconds too. Okay, great. Now we're going to need to make a change to this particular Git ignore. And hopefully soon, the reason why we're making this change becomes apparent. We're going to go ahead and add an exclamation mark and then objects.dvc. Now we have not yet produced any files that match this pattern. This is a recurring theme where oftentimes you need to know in advance what kinds of files may appear and whether or not you want to track them in your repository. In the worst case scenario, where you do not pre-specify something in your Git ignore and learn that you need to ignore it, there are of course ways to deal with this, and it's a very common situation. However, the better you can know what may appear ahead of time, the more prepared you can be and the fewer dangerous situations you may find yourself in. So let me go ahead and save this file. And let's go and see what is going on with our source control pane here. What does it say we have as changes? So the U means untracked. We do not currently track this in the Git repository. So again, we have the files that I copied over at the very beginning. We have the metadata for targets, and we have the Git ignore for targets as well. Okay, great. So we now have the ingredients ready to load DVC, but we have not actually initialized anything for DVC. First, I'm going to go ahead and make a commit here. So I'm going to go ahead and add everything here because all of this can go in the same commit, but it's very important you don't just blindly add all files that are ready. You want to make targeted calculated commits that actually mean something important as a discrete unit of incremental progress in your code base. So here, I'm going to add a message that I added initial files for targets, and I added DVC object ignore pattern. Now, one thing you'll see is that it gives you a warning that this is a pretty verbose commit message. Depending on where you work and your personal preference, people may want to keep the commit messages to a minimum, as the recommendation stated there, 50 characters or less. Some people prefer more verbose commit messages. In this case, it's fine because it's just me using this, but you always want to make sure to keep to a consistent pattern or standard when you're creating your commit messages. So now that that's ready, I'm going to go ahead and enter, and I can either get push from the command line or use these sync changes here. And we've been successful. One thing I just want to point out is the incredibly handy Git graph piece of the extension here, the source control extension, that will show us how our Git repository has changed over time, where the origin is currently at, and who is making these commits, and what branches are going on in your repo at any given point in time. So we see that commit I just made, and we see all of the changes that were loaded, the new files that were tracked with that commit. Okay, great. So I'm going to take a pause there and make sure there are no questions that are going on with the Git tracking that is happening with VS Code. Okay, so now we're ready to initialize DVC, or data version control. So if you want to download DVC, which I highly recommend you experiment with, you can go to dvc.org and you can download, and there are downloaders for all of the common operating systems. I also highly recommend the overview documentation here. There is a short course that will explain how you can use DVC. And what I'm going to show is going to only scratch the surface of the functionality, but it will give you a flavor for why this can be such a powerful tool and why you really need to be thinking about versioning your data in the first place. So again, I highly recommend you go ahead and grab that download, which I've already done. And we're going to instantiate a DVC repo. So in order to do this, we're going to go back to our shell, and we're going to type dvc init. Okay, great. So something just happened, as we can see. There's a pop-up. The Git graph tells us there are uncommitted changes, and it's unsure of who made them and what commit it's associated with because it hasn't been committed yet. If we go here to the pane, we see several new things have popped up. We see a Dvc Ignore. We see our Git Ignore here, DVC, and a config. So if I go to the overall file explorer, we see there's actually a full new directory here, .dvc. We see tmp, which we won't go into the details of. We see config here, where it's currently empty because we haven't set anything like a remote for DVC or any other configuration options. And again, we see another Git Ignore. Here, we see that the cache folder is in the Git Ignore, and this is fairly critical to understand, that DVC is not going to check in data in Git. And this is really important because Git is not designed to version data at all. Git has file size limits, repositories must be within a certain amount of memory consumption, and it's just overall a bad idea to try and use Git to track things like your data, even if you have very small pieces of data. DVC is much better suited for this, but it's very important to understand that DVC is going to go and manage your data and version control differently than Git, in that DVC doesn't actually save all the versions of your data in Git. What DVC does is it creates pointers to that data, and you save snapshots of metadata that allow DVC to understand in any particular Git commit what version of your data to go and fetch from your remote repository. And it is your remote repository, or if you're using DVC locally, your local DVC cache data store that actually contains all the versions of your data. So I'm going to pause there and make sure, because that's a fairly critical piece to all of this, that we're not checking in our data to Git itself. Okay, so now that we have DVC initialized, the question is, what do we do with it? What are we going to go ahead and check into DVC? Now, again, this is personal preference, but in this case, when I use DVC with targets, I often like to use DVC on the entirety of the target's objects collections. So DVC allows us to add either individual files, which can be incredibly powerful if you're versioning, for example, a final report or a canonical model matrix dataset, or we can go ahead and check entire directories into DVC. The way we do this is via the following command. It's DVC add, and then the name of whatever you're going to go ahead and add to DVC. So in this case, I want to add targets and then objects, the directory. In addition to this, I also want to add reports and then regression diagnostics, the name of my report, .html. Now, that file does not yet exist because I have not rendered my report. But when I add it to DVC, I'm able to track it nonetheless. Okay, great. So here we see that a few things again have changed. Inside targets, we see that objects is still the same, However, we have an objects.dvc file that has been added. And again, we see that in green because it is untracked in Git, and VS Code has recognized that this is untracked in Git. And right now, because it's not ignored, we want to go ahead and track that. These files, these .dvc files, are the files that allows DVC to converse and understand what version of data you're going to fetch. When we inspect one, we see that it has an MD5 checksum. We see that it has size, end files, and path, but that's it. It's merely a small metadata file, and this is the unique signature of this particular DVC file. So this file, objects.dvc, is actually what goes into Git, and this is what we continue to version control and maintain. Okay, great. So I'm going to take a pause there and make sure everybody understands what the nature of this DVC file is. Okay, fantastic. So we're going to go ahead and make another commit. Now, if we scroll over, we see in functions.r, we have built a model on only women. Now, let's suppose that this was the way our experiment began. We thought we wanted to only include women because that was what was pertinent to this model building exercise. To parallel the example I gave in the initial presentation, what if we find out midway through our experimental life cycle that our investigators are interested in men as opposed to women? So if you think to yourself about what would have happened if you did not use a system like this, all of a sudden you realize that your data may be decoupled from the scripts you're using, you may have multiple references to data, and it gets messy very fast. When you're using DVC and targets in conjunction, it allows us to make changes like this very swiftly and very robustly. So again, let's go ahead and make this commit. And remember that when we ran the tar make future function, we ran this version of the pipeline where gender was equal to F. So here we're going to go ahead and say, first model version, women only. Okay, so let's add, everything is staged, and let's add these two pieces, the objects DVC and regression diagnostics. Okay, everything is staged. We can go ahead and commit that, sync our changes, and let's take a look at the graph right now. And we see that the message here, first model version, women only. So this is the current state of our repository. We have now initialized DVC. DVC has a pointer to the versions of all of the target objects that are currently in this targets objects folder. And the objects in this folder correspond to the version of our pipeline that was run on women only. Let's briefly go back here and take a look at our R console. Let's inspect the actual model summary itself and get a feel for what it currently contains. We can do this via the summary tar read and then make model command. Scrolling up, we see that when you call summary over a linear regression model object in R, you get the residual distribution, quartiles here. You get the coefficients, including the coefficient on age, 15,112, standard information and t-test values, significance values, p-values, etc. This shows us that, again, we can always read in any particular target that was part of our pipeline and interact with it like we would any variable in our R session. So let's keep this number in mind, age and 15,000, because we're going to want to compare the results of this when we change our pipeline and understand where we're actually pulling new versions of data from and why it's important to keep things organized using DVC and targets. I'm going to take another pause here. So now we have a repository in a state where we designed a pipeline, we visualized it, we actually ran that pipeline with a given configuration of parameters, filtering decisions, assumptions, etc. We also have a DVC snapshot that pertains to that run of the pipeline. we've created a pointer to all of versions of the targets in that pipeline. At this point, the repository can get a tag, which denotes the particular version of the pipeline and associated data objects at a given point in time. So in order to do this, we're going to go ahead to the command line, and we're going to use the git tag command. And when you use the git tag command, it's going to assign a tag to whatever commit you're currently checked out on. So if we type git tag A, and then we're going to call this v1.0 because this will be version 1.0 of our pipeline and associated model. And we're going to give it a message that says model version 1.0, women only. So the goal here with the tag is to freeze the entire repository at a moment in time and say this is an end-to-end encapsulation of all of the decision-making, documentation, artifacts, results, visualizations, and discussion for a set of assumptions or parameters when you're running an experiment. And this is the power here, where we're able to combine all of these things in an easy-to-reference way. So if we take a look at our actual commit, we see that the commit itself is the same. This actual commit designator did not change. If I expand this a little bit, and maybe close my viewers, you see that there's now a v1.0 tag. So this is the git tag. And we see its first model version, women only, is the message. And we can actually use Git Lens and its integration with VS Code to investigate the tags. So here we see we have a list of our current tags, v1.0. And if we had multiple tags, which as you'll see soon, they would all be listed here. And these multiple tags allow us to understand that in any given tag, we have combined the scripts, the assumptions, the filtering decisions, the data itself, and the reports, all in the same environment. So that when we check out a tag or we share a tag with our colleagues or even ourselves, if we're trying to reference prior work, we have a guarantee of understanding what code produced the results that we're currently looking at. So if we look at any given tag, we can also see the commit lineage that led to that tag, how it builds off of prior work. And whatever the most recent commit is that produced a tag, here showing us that we added all of these files for that tag. So hopefully that makes sense. I'm going to pause again here because this is a fairly important idea, the usage of tags in Git. And this is also a mechanism that is commonly used when you're versioning entire repositories themselves, not just pipelines. So when you're releasing versions of a piece of software, it's common to have a versioning scheme, such as v1.0.0.0 or v1.0.0.1. And these increments, again, are going to be dictated by the environment with which you work, your personal preference, and standards set by your group. But if you can define a versioning scheme that makes sense, where the major and minor versions of your tags mean something, and you document those changes, and you document the different versions, when you combine all of this, it's very easy to reference the entire lineage of a project without trying to crawl through a Git graph and multiple branches and random files scattered in emails. Instead, you can consult the versioning, the major and minor versions of your pipelines and experimental runs, and then check out those commits directly or cross-reference those data files or results directly. And when you're looking at those reports, again, you have an absolute understanding of what code and environments produced the results that you're looking at. So again, we've created a Git tag, we've put it on our most recent commit, and this helps us freeze this moment in time and cross-reference it. It allows us to, years down the line, understand at this commit, it was our first model version, and the defining characteristic of that model was that we only selected women for fitting the linear regression. Again, this is my personal preference to use this as the descriptor, but you can be as descriptive as you like with Git tag messages. You could have many lines or hundreds of characters to describe any given tag or model and pipeline version number. It's up to you, and it's up to the efficiency and working patterns of your team to arrive at a decision when you use a scheme like this. Okay, great. So we see this in the Git graph. We see this in the Explorer here in GitLens to see the different tag listing. So now we're going to go ahead and explore that scenario that I was referencing before. We feel like we have the model in a good place, but then we hear from our supervisor, this is wrong. We want to pivot for some reason. We believe we should only fit this model using men. Now, this may seem like a contrived example, but this happens all the time, where a filtering decision or a raw data source is proposed as an alternative, and you have to very quickly accommodate this proposed change and be ready to revert back in case people flip-flop, which again is an incredibly common scenario. So let's go ahead and actually implement that code change. Let's say we took that advice to heart and we say, okay, great, we will implement that change and modify our filtering decision. Instead of F, we're going to use M, which is for men. Let's go ahead and save. And first of all, you see we get a nice git blame that says, you 4 seconds ago uncommitted changes. That allows me to know I actually just modified that line. If we go to any other line, we see you 21 minutes ago and the message of the commit that corresponds to that git blame. So this is another powerful feature of VS Code. It allows us to have these inline git blame annotations that makes it fairly simple to understand who modified what pieces of code when you're looking at a fresh file in your Explorer here. So again, we made this modification, we swapped F to M, and all that does is instead of using women in the linear regression, it now uses men. It's an alternate filtering decision. We see that VS Code has detected this change, functions.r. We see that we have a little badge icon as well. If we click this, we can actually see the diff. We can see that there is red here. We've modified this and removed something, and we've added this line instead. So we can compare these files side by side and see what have we changed exactly. It actually highlights this if you look closely, F to M. Okay, so now we have a change here. And the question is, how do we understand how this impacts our pipeline? Well, let's go ahead and run our favorite function, tar viz network. We see we have a viewer pop up. We see something different now. So we see get model summary, model predictions, and raw data are all still this black or gray color. They have not changed. Yet we see get healthcare by age is now this blue color. The reason being, we've actually modified this function. Targets performed a static code analysis, and it parsed the fact that we've swapped the F to an M, and that this file is actually different now. This particular function has changed its behavior, and thus the definition of the target has changed. This now makes all resulting dependencies of this target outdated. So we see not only is get healthcare by age blue because it's changed, all of its downstream dependencies are blue because they're outdated. So we don't need to modify these two functions because they're the same, but we see that all of these targets depend on a new model. So because we've changed the data that goes into our model, of course, the model itself is going to be different because we have a different set of assumptions or filtering decisions in the data that's going in as the input. Once the model has changed, of course, the report referencing the model, the predictions of the model, and the summary of the model will all be changing as well. So tar viz network is a very powerful tool to allow you to understand as you are working in real time, what is changing about your pipeline. Perhaps it illuminates a dependency structure that you didn't quite understand because it's been a long time since you've worked on the project, it grows in scope and complexity, and you have multiple people working on distinct arms of the project that you were not aware of. When you run tar viz network, it pulls the repo at a current point in time, and it says which of these need to be rerun, which of these are outdated. And now we're going to see when we rerun it, that's another hugely powerful part of the target's experience in most of these pipeline management tools, is that they allow you to skip all of the targets that are still up to date. In particular, reading in the raw data in this case does not need to be done twice because it's already been parsed, it's already been read. So imagine you had a massive raw data file that was dozens or hundreds of gigabytes large. It would be a real pain to have to read that in every single time if you didn't actually change anything about the raw data itself. Targets intelligently understands when something has changed or been modified so that you don't end up doing redundant and inefficient work. Instead, you focus on the parts of the compute process that do need to be rerun and all of those dependencies too. So I'm just going to take a second and make sure everybody is familiar and acclimated with this updated version of the visualized network. Okay, great. So now we know that there are outdated targets, and now we know that we can run tar make. And in this case, again, I'm not using tar make future. I'm just going to use tar make. And let's go and check out what we see at the beginning. We see skip target raw data. So in the summary reporting of targets, we actually are told what targets has skipped and what it has to build again. And here we see again that it built the make model because the make model is outdated since the function defining this target has changed. Okay, great. We also see that the pipeline ran faster than last time. And one of the reasons why is because we've skipped parts of the pipeline that did not change. This is a trivial speedup in this case, but again, in reality, this ends up saving a huge amount of time because often when we repeat our data science experiments, we run everything from scratch every single time in order to safeguard against missing important components. The other reason why we may need to do this is because our code is often written in spaghetti style, where there are multiple chain dependencies that require manual launching of certain notebooks, certain code chunks, certain pieces of code that require us to take a principled manual approach towards rendering a certain set of outputs. Instead, when you define a targets pipeline, you always run the entire pipeline by default, but you skip all of the pieces that, again, are already up to date. So this is the best of both worlds, in my opinion, and one of the reasons why I think using tools like this are so powerful. Again, I want to reiterate this point that targets is simply one way of doing this. As you saw in the precursor to this demo, there are hundreds of available pipeline management tools for your language of choice, whether that be R or Python, or even if you're just doing bash scripting. I just want to make that a very clear point that it's not about the specifics of the target syntax, although I think there are some amazing benefits in particular with the targets package, but it's the idea of constructing these pipelines. Most of these pipeline tools will have the same kinds of functionality, where you can get visualizations of the DAG, where you can define the chain of dependencies in an easy to understand list object, etc. Targets is merely my most familiar way of performing this kind of pipeline decomposition. And I find that it has, again, a huge edge up on competing packages because of some of its extended functionality, which unfortunately we will not get to cover in the scope of this demo. Okay, so we've made our pipeline again, and let's look at the changes that are induced when we make that pipeline. Again, functions.r is waiting to be committed because I switched the gender that was being referenced from F to M, but now we also see meta has changed. And the reason why is because targets has detected that the objects in the targets directory have changed because we just instantiated a new run. We have a new tracker for what the current iteration of the pipeline is. And so that's the reason why we have detected in VS Code that that file is waiting to be changed. So now let's go ahead and run summary tar read make model. Now, when we inspect this output and compare it to the output that we saw before, we see a very key difference. We see that the age coefficient estimate is actually lower. It's 13,000 now, as opposed to what we saw above, which was 15,000. This shows us that even though we're reading in the same object name, the version is different. And this is the key, is that instead of creating two forked versions of that data, where we had make model 1 or make model F, and make model 2 or make model M, it's simply make model. And we handle the tracking in an organized way that multiple people can understand, even if they were not the authors of that code or data object. So again, let's just compare. The call is identical. It's summary tar read make model. Yet when I run it here, I get a totally different answer. This does not overwrite the contents of the previous make model. The reason being is that we have actually saved via DVC's pointers the other versions of make model as a target. And I'm going to demonstrate this soon. So I'm going to take a pause there and make sure that that idea is solidified for everybody as well. Okay, great. So now we have an updated targets run, but we do not yet have an updated DVC snapshot. DVC is only tracking the first version of the data that we've had. So we have to repeat the same commands that we did before. So you see here, we ran DVC add targets objects and reports regression diagnostics HTML. And we're going to go ahead and do that exact same thing. DVC add targets objects, and then our report, the regression diagnostics.html. Oh, and I have an error here because I did not specify my path. So I'm going to repeat that, DVC add targets and objects. And reports, regression diagnostics, HTML. Okay, so these two have been added again. And now we see that we have detected two changes, and these are the DVC files that are pointers to that snapshot of the recently updated versions of both the objects directory that contains all of the target object data files and our report itself, regression diagnostics HTML. So every time you have another snapshot in DVC that you're ready to commit to your cache, you go ahead and you add the files or directories that are of interest, and DVC creates an updated .dvc file associated with every item that you add in the DVC command. So that's how we've arrived here again with these changes. And we're ready to go ahead and add these changes. Great. So now we have another model. So updated model, men only. Again, I'm deviating from the style, and here I have a brief typo and fix that. So I'm deviating from the style of the other commit message. And in general, you want to make sure that you have common guidelines for creating your commit messages, partially to make it make sense to other people you're collaborating with, but also to make things searchable, so that if you're ever confused and a project has grown where you have thousands or maybe even tens of thousands of commits for huge projects, you're able to have an organized way of searching for where certain things may have happened or certain branches were created or merged back in. So I'm going to go ahead and add those and sync my changes. And let's take a look at the Git graph. And we see, let me close this viewer, that we have a new commit, updated model, men only, and that's contrasted with the first model version, women only. Now, again, let's just, as a sanity check, inspect the visualized network. And now again, we see everything is up to date. There is no blue here, and that's because we just ran tar make, and it has incorporated all of the changes. When a static code analysis was run, we have not detected any updates that need to be reflected in the targets pipeline. So now we're up to date here, and we're ready to go ahead and create another Git tag. So it's going to work exactly the same way as before. We're going to do git tag a v1.1. So I'm choosing this kind of major minor versioning scheme. So minor versions in this case are filtering decisions, and perhaps major versions may be different model structural choices, instead of linear regression, for example, fitting a generalized additive model. In this case, because it's a fairly small filtering decision, this is going to be incrementing the minor version. So git tag a v1.1, and we're going to go ahead and give that a message. It's always a good idea to give your tags messages, make them descriptive. Model version 1.1, and here we have men only. Okay, so now we have a tag. We see that just popped up, that's reflected here. Close the viewer. v1.0, v1.1, and in Git Lens, we see two different tags. We see the lineage of each of those tags. Because these are both progressing in the same main branch, they have the same lineage. And this one ends here at first model version women only. So again, this is a great way to understand what kinds of tags are being accumulated in a repository. And you can sort these and you can list them and do other more advanced functionalities with them. But I just want to point this out in that this is why tags are so useful for somebody like me, where it's very easy for me to see an itemized list like this and understand how all of the different changes to your pipeline and data files took place over time. We also see there are some date timestamps here, which is tremendously useful so that we can reference this further down the line or link them to, for example, email threads if you want to know roughly what time period did a piece of work take place. It's always useful to have timestamps as well as the Git blames that say who actually created that tag or who created a pull request and accepted it. Okay, great. So we have our two different tags, two different versions, and now what I want to do is showcase some of the behavior here by going to our interactive terminal. And again, if we go and run up here, the summary tar read make model, just copy and paste this. We see 13425, which reflects, again, this most recent version, 13425 and 13425. So that's the current version right now. So whenever we run code, that is the version that's being referenced. This is right now the men-only version of the model. We're on v1.1. Now what we can do is we can check out a prior tag. This is a prior snapshot of our repository as a whole. So let's see how we do this. In order to do this, we can go, for example, to Git and then check out, which can be used to check out branches, but in this case, we're going to use it to check out an actual tag. Okay, so we've checked it out. A few things have changed. We get a helpful warning message that we're in a detached head state where we can look around, make experimental changes and commit them without impacting any branches, etc. But it's important to understand we're in a detached head state. Sequencing does not work as you may expect it. Here we see that we're in v1.0, so it's helpful to understand. Before it said we were in main, right now we're checked out in a specific tag, so a specific commit. The graph itself also shows you where you're currently checked out by this hollow circle. And also, just as a brief point, it also says, again, where your remote currently is, what has been pushed to your remote. So our remote or GitHub is up to date with everything else. As we see, it is on the most recent commit here, the origin. So back to this main point, it tells us the message here and the commit string. And now when we look at these files, these are all files that reference that particular version of the commit, the v1.0. If we look at functions.r, now that we've checked it out, even though I haven't opened or closed this file, we see gender equals F. And if we click here, we see the git blame annotation, we see the actual unique identifier of the commit, we see who did it, the timestamp, etc. So we've checked out the information, but we're not done yet. We also need to run a specific command, and that is Dvc Checkout. Now, when we run Dvc Checkout, what this does is very similar to when Git checks out to a tag. Dvc swaps its pointer so that it understands now that there's a different Dvc file associated with the commit, it references new data in the cache to correspond to the prior versions or runs of these objects. So now that we've run Dvc Checkout, let's go ahead and run that same command that we just ran. So again, remember, prior to this, it was 13425. When I run it now, it's 15112 again. The reason why this works is because we are now referencing different data. Even though I did not rerun my pipeline, I did not run tar make in between, I have successfully recovered my old data. The way I did this was by checking out to a prior tag, the v1.0. I knew to check out to this tag because I was documenting what the major and minor versions of my tags correspond to. Let's say somebody asked me for that version of the model. I check it out via the checkout command in Git. Then I also run Dvc Checkout to make sure that when I check out to a prior version of a commit, Dvc properly points to the older version of data that is also associated with that commit. This also implies that you need these Dvc files in your commits in order for Dvc to work correctly. So do not delete these, do not lose these, and do not corrupt these. These are the pointers that allow Dvc to reconcile older versions of your data as you run that Dvc Checkout command. So that about covers what I wanted to show. Hopefully this shows some of the utility of this kind of approach. where this was an incredibly simple change, but had I not set things up this way, I would have had a very complicated picture in managing multiple versions of data, multiple versions of code. Now that I have it structured this way, I know that I have two different tags. Again, we'll view them here, one for men only, one for women only, and corresponding to these different model versions. I know I can swap back and forth between them, mix and match code between them in a new branch and merge that back to my main branch. And I also know that DVC has persisted a snapshot of the data that I care about to version. DVC did this not by checking in data into Git, but by checking the pointer files into Git. And whenever we go to a previous commit or an alternate commit, we run the Dvc Checkout command to ensure that DVC swaps the data that's currently being used to correspond to whatever version of the DVC file we are checked out on a particular commit or tag. In that chain, that is how we've arrived at having this age 15112, despite the fact I didn't need to recreate the pipeline. I'm actually reading in a previous version of the data, again, even though the file name is identical. This is also a word of caution in that the file name is identical. So by just looking at the file name, you do not have the requisite information to understand when it was created, what it corresponds to, etc. And that's a temptation people often suffer from when they create file names that have, for example, dates in them, or author names in them, or motivating factors in the data itself. For example, if we had called it make model women and make model men. This is an extremely dangerous proposition, as I mentioned to before this. And the reason why is because it quickly spirals in complexity, and it's a terrible management system moving forward to have a guarantee that you can always reconcile what code produced what data. It's far better to use these tools like DVC and targets to ensure that even though your file name is the same, you always have the metadata necessary to understand what you're reading in. You can always know what you're reading in by saying, what Git commit or tag am I currently checked out on? And did I run Dvc Checkout? And what is the metadata of my DVC file that I'm currently reading in? By keeping those pieces organized and by making sure you stick to a standard throughout the lifecycle of your projects, you can avoid immense pain in the future by adopting these guiding principles. One last thing that I wanted to demo is showcasing what DVC is doing on my local storage. Here I'm going to run the du disk usage command, and what du does is it helps me understand what is the memory consumption of any given directory. So here, if I run du and then flag sh, and then ./.dvc/cache, and then another slash, we see the memory consumption of the current DVC cache. So in this case, just 2.2 megabytes. So what the DVC cache is doing behind the scenes is locally on my computer, it is accumulating all the versions of all of the data that I've checked in the DVC. Now, I am only keeping this locally right now, but DVC connects to any SSH target, it connects to AWS, Google, etc. So all of the common cloud providers, you can host backups of all of your data via this method, where instead of locally keeping your cache, you can actually designate a DVC remote, similar to how I use GitHub as my remote. By setting a DVC remote, you're able to not only keep a local copy of all versions of your data, but a backup of all of that data on a remote server, such that if your computer breaks, similarly with your GitHub code, you can always recover it and load it on a new machine and interoperate with teams. And that's another important point, is that these tools help you work with teams way more effectively. The reason being is you always have control and an understanding of what was created when, and hopefully why, if you're documenting properly. So this is going to be the close of this demo, and hopefully you found it instructive and have an incentive to go out and try these tools for yourself. And as always, as per my recommendations, experiment with these tools. I've only scraped the surface of the functionality of both DVC and targets, and both have so much more to offer. In addition, if you're a Python-centric programmer, I at this point have given some recommendations on pipeline tools such as SnakeMake that do very similar things to targets. However, in my opinion, Targets has some main advantages over these tools, and I am biased because I'm an R programmer to begin with. So hopefully you enjoyed the talk, and looking forward to answering any potential questions you may have. Thanks.